and you can start to think of it right now. There are two effects that are going on. There is one effect which is the top surface basically trying to push things. The other aspect is that as you are going in a radial direction, the area is also increasing. You are going through a larger gap. The gap is increasing, right? H of r is basically larger as you are radially moving outwards, which means you need to pump fluid through a larger surface area than what it was at a smaller r. So, there will be a compensatory effect in order terms of how rapidly should u of r be at different radial location, and then to add on to that you are also pushing the top surface. One is you are thinking of a channel flow through a non-uniform cross section or non-uniform where the walls are diverging, the other is where the walls are also moving. So, you have these two effects taken simultaneously in this. Now, so how do I find pressure? Because without the actual calculation of pressure, I cannot have the calculation of force or finding that numerical factor. So, we have used momentum conservation. What is left now? Continuity, mass conservation. So, mass conservation, you can go back to your very elementary understanding of mass conservation, which is using a control volume. Think of a control volume, and that even though I am saying it is elementary, it is actually very powerful. Think of a control volume where the fluid is rushing out through this cylinder at a given r. What is the mass flux through that region? How do I find that? If I say that is Q out, how do I calculate that? Rho 2 pi r u r dz, z going from z1 to z2, right. On that surface I have a radial velocity which is going outward. So, I take a small cylindrical strip of height dz at a radius r. So, that surface area is 2 pi r dz, find the flux through that and integrate it over the entire region going from z equals z1 to z equals z2. So, you have to do the integral, and obviously you have an advantage here that dp dr is not a function of z, the only dependence on z is appearing here. So, I will take out all the terms that are constant, and by doing this you are going to get rho 2 pi 1 by 2 mu dp dr into 1 by 6 z1 minus z2 cube. It is just doing an integration. What is z1 minus z2? H. So, I can again write this as 2 pi rho, let me just cancel. So, pi rho mu dp dr h cube by 6. Okay, that is the mass flux that is coming out. Now, what compensates for this? Motion of the top surface, right. The top surface is mobile, the top surface is moving, it is the motion. So, you can think of it in terms of the fact that the control volume itself is changing. The volume is decreasing or increasing depending on whether it is approaching or retreating. So, the rate of change of the control volume gives you the mass flux through the control surfaces. That is all that we are doing here. So, what is the change of the volume? Even though it looks very complicated, what is the change of the volume?
W naught into pi r square.
Why is it W naught into pi r square, not something more complicated?
The projection of area.
Because the top surface, even though it is curved, it is moving only in the z direction. right. So, if you are trying to find out by how much that volume is changing, it is just the projection of that area. So, W naught into pi r square times rho, and the sign will be, what should be the sign? Negative if it is moving towards, right. If they are moving towards each other, then it should be negative. So, this is equal to, I have missed an r here, pi r. So, this should be equal to pi r rho by mu dp dr h cube by 6. So, this gives me dp dr is equal to minus 6 mu w naught r by h of r cube. Do we know h of r? The initial paraboloid, right? H naught cube plus 1 by r square okay. Now, how do I find pressure? Integrate obviously. So, pressure at some r minus pressure at a large distance which I will take as infinity. So, what I am saying here is that when I am integrating from r to a distance sufficiently large away. So, this becomes r to infinity. Instead of r, the dummy variable, I will write as an h here, and this is the pressure which is sufficiently far away. So, I will assume that far away from the gap, this is, I will equate it to 0, and this becomes r to infinity. Now, what does infinity mean here? What is the radial scale? So, infinity here means that you are at distances which are much larger than r naught. It is not that you necessarily have to be infinitely far away from the sphere. You need to be far enough such that you are larger than that radial length scale. That is the meaning of infinity here. So, you can do this integral, it is not too hard. You can write this as some z equals, or not z, we have already used z. You can probably say some q is equal to 1 plus, this is s square 2a h naught, and then perform that integral. So, P of r is 3 mu w naught by a epsilon square 1 plus r square 2a square epsilon. So, h naught I am writing as a epsilon. This is the pressure field. This is the pressure field at any radial location. And as we have already argued that the viscous stresses in this particular problem are weaker than the pressure contribution. So, all we have to do now is find the force or the lubrication force which is going from r equal to 0 to r approaching infinity, P of r 2 pi r dr. Right. This is over one of the surfaces. You are trying to calculate over one of the surfaces of the sphere, because with respect to that local coordinate system, the surface of the sphere is going to extend all the way to r equal to infinity. That is the reason why I am putting here r going to infinity. You imagine this local coordinate system, right. So, how do you integrate it over any of these surfaces? So, from it goes from 0, but then by the time you are approaching the outer region, r is going to in that scale approach as infinity, because you have scaled your variables, right. You are looking at variables that are scaled. So, or 6 pi mu a w naught divided by epsilon. So, the force on one of the spheres, or in this case the bottom sphere, is this. For the other sphere it will be exactly opposite of that. So, the entire exercise here was to find 6 pi. You could have probably guessed it in advance by just taking a from your isolated sphere calculation, but it tells you that you have a contribution that is coming which diverges as epsilon goes to 0. So, now there are few questions to answer. Obviously, we have solved the problem in the gap, but there is also a flow away from the gap. If the spheres are moving, there is also flow happening away from the gap. That is also going to have its own contribution to pressure, stresses, and thus force. What about those contributions? You have a sphere moving with velocity w close to the second sphere which is held stationary. So, now let us say I am trying to find the drag force on this sphere. What I have found is that the drag force that it experiences is on the second sphere, if I write F2, is minus 6 pi mu a w naught epsilon inverse. So, there is a sphere which is moving towards another sphere which is held stationary, it is moving with w naught, and I find this as the force. What about, so we have only focused on the contribution from this region, that is all we have done, but there is also the remaining part, right. The remaining part, on the remaining part the scale of pressure and viscous stress is going to be mu w naught by a, which means the force contribution from the remaining part is going to be mu w naught a, whereas from the gap it is going to be mu w naught a by epsilon. So, between the two the gap is dominating. So, when the gap gets smaller and smaller, the lubrication contribution is going to dominate over the outer region contribution. So, if you want to refine this, you need to know about the outer problem, which we did not do. We never did any outer problem here. We never calculated the outer problem here. So, you need to know the outer problem if you want to refine this approximation, but the leading approximation is when epsilon goes to 0, the lubrication force or the force acting on a particular sphere is going to become infinitely large. So, you can see that the far field and the near field have very different effects on the motion of the particle. For instance, here if you now want to take this problem and do it like a mobility problem, like what we did in the last class, this was stationary and this was a, I think this was a question someone had asked. If this is moving under a fixed force, what should be the velocity?
That was the last approach, right?
Yeah, but we are now asking this question from a lubrication point of view, that in the last approach we did not really discuss anything about motion along the line joining the center or motion joining. In the end we found the correct connection to the settling velocities, but right now I am saying that let us revisit that problem of them trying to move along the line joining the center and ask the question that what would be the velocity of the moving sphere with respect to the stationary one. So, I am going to a reference frame where sphere 1 is stationary and sphere 2 is moving with respect to it, and sphere 2 is experiencing a constant force. So, which would give me W naught by epsilon is equal to minus F by 6 pi mu a, right. Now, W naught is due to the rate of change of the gap. It again depends on how we have defined W naught pointing downwards. That means that as the gap becomes smaller and smaller, W naught is basically plus dH naught dt. And what is epsilon? H naught by A, right. So, this is right. So, what would be the solution to this? H naught of t would be H naught of 0 exponential of minus f by 6 pi mu a square into t. What is your conclusion? If you plot H naught of t by H naught of 0 as a function of time, it will start from 1 and then decrease exponentially. So, when would it actually go to 0? Infinite time. So, contact happens in infinite time. So, lubrication effects are so strong that two spheres. So, this is like if I drop this pen, it is not a sphere, but if you imagine I have dropped this pen, what is the time it will take for it to touch this wooden desk? Lubrication theory tells us it should be infinite time. So, now the question is, you obviously you do not need to do fluid mechanics, you know it did make contact, right. There was a sound that came, it did make contact. So, the question is, what then enables the contact? If lubrication theory is telling us that it is impossible for me, because you would need infinite force for contact, right. If you go back to the expression of lubrication force, if epsilon goes to 0, you need infinite force for there being contact. So, how do you end up basically getting contact? So, body force is what is driving the motion, but what would actually enable the contact?
Internal forces which will overcome the
Something that is not there in the model, that is the first way to think about it. We have not captured what is enabling contact, because this is our model, right. We took Stokes' equation, we worked with everything and then we have arrived at this particular answer. So, clearly something that is not captured in this model is enabling contact, and that something is all kinds of things that is beyond and besides hydrodynamics. So, there can be interparticle forces like van der Waals forces, there can be surface roughness, the surface is not perfectly smooth. So, as they get closer you can think of like a lot of gear kind of teeth shape which are actually interlocking with each other, all kinds of effects can be there which is not there, and that enables the contact. And again, for an object this big, there is also the important point that there is a finite amount of particle inertia that is there. We have not accounted for it. So, but in general the idea of lubrication forces and how lubrication forces play a role is very important for you to understand, because this tells you that lubrication effects can be very severe when you are looking at small scale objects in terms of preventing contact or preventing collisions between objects.
So if we consider, if we want to incorporate that kind of forces, so should we add something in the hydrodynamics?
Yeah, so you don't add in the hydrodynamics necessarily, but you add it somewhere here. There is a little bit of unknown stuff here which is not there in this model. The relative velocity between the two surfaces can be mediated or can be influenced by other physics which is not there here. So, this is all that we have to discuss regarding the normal motion. As I had mentioned in the beginning, I am not going to derive the tangential motion calculation, which is a motion of this kind. The approach remains similar. You assume the same kind of scale separation in the radial and axial direction, but I am going to write down what would be your scale for your force. That would be mu W naught A. This did not require you to know anything. This is the scale for the force in the problem, but the divergence is actually weaker. It is not 1 by epsilon is what you get from the squeeze flow problem. So, it need not just be two spheres, it can be a sphere and a flat surface, because that is like one small sphere and another sphere which is infinitely large, whereas this one is a sphere which is trying to move with a velocity with respect to another stationary surface. So, here the divergence is logarithmic in the separation, and log, as you can already guess, diverges much weaker than a regular inverse power. So, this is basically the near field interaction part, which I thought is again an interesting bit you should know. And whatever I did here today, the starting point was the Stokes flow equations, but you can go back and check that the terms that we have not taken here into account, as the gap gets smaller and smaller, those inertial acceleration terms actually become negligible. So, even if you were to start off with the Navier-Stokes equation, the Reynolds number based on the gap becomes negligible, and thus the entire derivation that we have done today will also be applicable if at the scale of the particle it is not a Stokes flow problem. Right now our starting point was at the scale of an isolated sphere, it is a Stokes flow problem, and then we are doing this gap problem. What if the problem was not Stokes flow at the scale of the isolated sphere? Even then, as the gap gets smaller, the determining Reynolds number is not based on the Reynolds number of the object, but rather based on the gap, and that becomes negligible, and so you can still continue dropping the inertial terms and this process continues, which is why this is far more universal than how I may have probably presented in the beginning. So, you have a picture of doing this calculation in the far field using method of reflections, and you have a picture here at least done in detail for the squeeze flow and some qualitative way for the shear flow part in the near field picture. So, obviously, as you can imagine that what lies in between is a lot of numerical calculation, but you have a feel for what is going on. Okay. Yeah.
If you do a simulation
Yeah.
of this kind of setup, so in that simulation,
This kind of setup as in
one body will be fixed and another will be falling.
a ball falling towards the surface. Yes.
So hydrodynamically it is not possible to touch, right?
Based on how you have modeled this, correct.
Yes. So in the simulation there is result what we will see? It will touch or not?
So, your simulations you need to basically put in something regarding what happens when the two surfaces. So, let us say that when you are solving this in a simulation, if your solving in simulation means what? Are you solving the motion of the one of the body? Let us say there is a spherical particle, there is a wall. So, if you are solving the motion of the spherical particle, at every instant of time you are computing what is the force that is acting on the object. Now, obviously that the total force is remaining fixed, which means that its velocity gets updated, right. So, now if you keep moving the object at some time step, you need to apply a collision rule. In every simulation there needs to be a collision rule that you need to incorporate, or you need to model the lubrication effects in a very detailed manner, where when the gap becomes considerably smaller, the force that you are calculating will only be accurate if you are well resolving the gap. See, you have understood here that the contribution to the force is dominated by what is there in the gap. The outer region is going to become more and more subdominant as the gap becomes smaller. So, obviously if you have only very few grid points between the bottom surface and the wall, automatically you are going to start not resolving the force accurately. So, that is something which is usually a big challenge. So, in a lot of simulations, one of the challenges that come in is if the objects are not massive, Stokes number is not very large, then incorporating interactions through contact is a tough thing to do. If you have particle inertia, and this again I would encourage you to think about it, lubrication does not kick in. Like here what I have done is I have said the object is falling and I have tried to basically find what the velocity is given the force. So, I have assumed that at every stage of the motion acceleration is absent, right. The particle acceleration, I am solving for an over damped equation. See here I am basically solving for an over damped equation. F is what? The weight of the particle. But actually what you should do is you should write down dw dt is equal to minus some function of the gap into w by tau p plus g. If your coordinate is pointing down. Now, if f of epsilon is the resistance that is there, which is the resistance to normal motion, which is blowing up as epsilon. So, f of epsilon goes as inverse epsilon as epsilon goes to 0. So, you will need to then actually solve something like this. I am given a reduced version of it, but there is obviously going to be a massive deceleration phase that is going on. So, if the particle acceleration is large or particle inertia is large, you cannot ignore this term. So, the lubrication effect actually kicks in at a much smaller gap, and you can compute what would be that gap or the non-dimensional gap based on this particle Stokes number. And in some cases if Stokes is order 1, you can find that the gap when lubrication kicks in becomes comparable to atomic length scale or comparable to length scale at which there is no meaning of doing a continuum simulation. So, those are again aspects which build on what we are doing, and they become more important when you are doing gas solid suspensions, where the interstitial medium is a gas like medium. For a liquid solid suspension, when the particles are not of very high inertia, the discussion that we had is reasonably an accurate picture of reality. Okay.